Hello, Andres. Welcome back.
Hello.
You try that again, Anders, because this time was not really very loud. But you should come here to the sitting space, and so we will be able to hear you better. Here the sound is 3D. You hear louder those who are closer to you. Hello. Good to see you, Jameson. Right. That's a good taste. We have 1, 2, 3, 4, 5 people on webcam. Let me just make a screenshot because after that I will ask everyone to switch their webcam off again to not to text the system too much. Thing is that I still consider this as an experimental session, even if everything seems to be working quite fine. But you know, this is the very first time that we use this server. The server we were using last year was in Europe, and this one is in the US. I believe it's in Texas. And the other difference, of course, is the software. It's not the same software. This is an open source version. I think a good 80% of the software is exactly the same, but the video modules have been changed because the video system that we were using last year could not be made open source. So that what the development team has done, they have integrated VLC within OpenQwaq. So now we are using the video system of VLC, and I think it's working quite fine. I'd like to ask Jameson, Natasha, and Weaver to switch their webcam off. That's it. 1. Now Natasha is switching herself off. I hope she will switch herself on again. On again. No, Natasha, you have not switched the webcam off. We can still see you. It's the 4th icon. Where is Tudor? So Mike is here. Okay. Natasha has switched the webcam off. Nino is here. Ciao, Nino. Tudor is here now.
Ciao,
Let's give
ciao,
some time to him.
Hi,
Ciao, Nino, benvenuto.
Everybody. Thank you very much, Giulio.
Thank you for coming.
Thanks to you and to Over.
Matvey, welcome. Who is managing this screening to the Russian students in the physics faculty? You should know, Suzanne, that you're going to have, I hope, a big audience in the physics department of one of the universities in Moscow. That should be transhuman.ru. Is that right? You can answer by chat.
Should we close our microphones too?
Yes, I would appreciate if everyone but Suzanne and me for the time being.
Okay.
Switch. Hello, Katerina. Good to see you. But now that we have seen you and I understand
Hello.
you
I
and
switched off my microphone.
great, and also your webcam, please. Perfect. You know, for the first part of the talk, we just leave the floor to Suzanne. Hello, Tudor. How are you? Good to see you. Everything is the same that you remember, so you don't have anything to learn, just use it. The software is different, but from the point of view of the user is the same. Yeah, since most of the people are in the US, I think you may experience this server faster as last year. For me, it's different because I am in Europe, but until now, this US server is working quite nice. I must have a lot of people here already. Okay, those who I don't know are user one. Thanks for coming. And I'm sorry, perhaps you are one of those who requested an individual access. I was not able to make many individual access, but I'll try to do better next time. Then we have user 12. Xaira is arriving. Xaira is here. Things must be still loading for her. I suggest waiting like 2 or 3 minutes before beginning. Yeah, nice sunny afternoon. As Anders say, here in Budapest is maybe even too nice because it's hot. User 12 has a delay. Frederic is still recording with a good connection. Let's wait for the last one, who is Eric, still in the lobby, and then as soon as Eric is here, we begin. Let me count to people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. Okay, so who switched their webcam on? That is Eric. Hello, Eric. Good to see you. And let me just give a last look to my email if some latecomers is not able to arrive. No, I think everything is set to go. I will start a recording and then give the floor to Suzanne. I'm going to start recording now. Suzanne, you make ready. Sorry for my dog who is misbehaving, but I'm going to switch my own microphone off anyway.
Julia, are you going to give an introduction to the new version, or shall I just start straight away?
Not really. You just start straight away when I give you the floor. Suzanne, you have the floor.
Okay, thanks, Julia. Well, Hi everyone. I'm really happy to be back in, well, what used to be Teleplace and is now an open source version. And I'm happy to be giving the first talk here. It's really cool. And so this talk is entitled Hack the Multiverse, as you should be able to see on the slides. And so the reason that I decided to give this talk is because this is what I do in my day job. I actually hack the multiverse. So you might wonder, what is hacking? And well, that's kind of defined as playing about with computer programming and stuff like that, finding out things, understanding how things work and such like. And what is the multiverse? Well, the multiverse is a concept that's well known within quantum mechanics and quantum physics. And what it is it's basically the idea of lots of parallel universes. So if parallel universes sound a little bit science fiction, a little bit strange, don't worry, because this talk is going to be a lot more down to earth, and I'm actually going to show you how to program the multiverse using quantum computers. So let's begin. So to understand quantum computing, we have to first start by thinking about conventional computing. And conventional computing is really something that we take for granted. We have very, very fast computers nowadays, and it's kind of, when you think about the kind of applications that we run on computers, it's quite amazing. I mean, we have these very, very high-level applications to do all kinds of things: web chat, streaming video, spreadsheets, massively multiplayer online games. It's pretty amazing. But when you think about what computers are doing right down at their core, they're actually all performing these very simple arithmetic operations. So you can basically think of your computer as a kind of a giant abacus that's running really, really fast. And the reason that we don't kind of see this every day is because these calculations are happening billions of times every second. And because of that sheer speed, we're able to run these kind of amazing applications. But what you have to remember is that under the hood, it's all just addition and subtraction going really, really fast. So this is how I like to think about conventional digital computing. And this is kind of an overview of all computing that exists today in the world. So we have some bit strings which come in at one end, and then what we're doing is we're supplying an arithmetic program which does some operations on those bit strings, and you get some different bit strings out. So this is kind of happening very, very quickly, but effectively what you're doing is you're just applying these very simple logic operations to these bits of information and transforming them into other bits of information. So this is really, really good for running most of those high-level applications that I was discussing, these amazing things we have today. But there are some other tasks that computers are still not very good at. And some of these tasks are things like image recognition, natural language processing, which is getting computers to talk back to people in a kind of natural way, and things like learning, so actually taking in information and learning from experience. So computers are really, really quite bad at these things still, even though we've been spending decades trying to solve these problems. And even on the small prototypes where this kind of thing does happen, and these kind of applications have been tried to be built, they're actually very inefficient. They consume lots of power. They use lots and lots of processing resources to do really simple things. So there's something wrong there. We actually seem to be taking the wrong approach to this in general. So what I'm going to ask is, can we rethink computing from the bottom up? Is there another way to do computing that doesn't involve these kind of arithmetic operations underneath? Is there something that we can replace those operations with to perform computing in a totally different way, a totally new way? So what quantum computing is, which is what I'm going to be talking about in this talk, is a totally new kind of computing. It really changes everything. And it changes everything from the ground up right to the very applications that we're writing using computers. So it uses new physics, which is quantum physics. And that's the best model of the universe that we understand. It's really our deepest understanding of the universe. So actually kind of baking that in to the way we compute is a really good idea because it's the best way that we understand the world. And then there's new hardware involved. So in order to use these quantum mechanical effects, we actually have to redesign the entirety of hardware and processors and how we actually build these things. And then most importantly, which is what I'm going to spend the second half of this talk talking about, is how we program these things is really radically different to anything you've seen before. So it's an entirely new way of programming, and it's really kind of interesting. So I hope you'll find that exciting. So the way that we do quantum computing at D-Wave is an approach called natural quantum computing. And the key difference between this quantum computing and conventional computing is that we're no longer talking in terms of bit strings going in, being transformed, and bit strings coming out. So you have to totally take that idea out of your head completely. This quantum computing approach is actually more about finding good arrangements or finding good configurations of bits of information. So throw out everything you know about computing and information now and kind of let's start from scratch and really talk about how we can compute totally differently with access to these quantum physics resources. Whoops, missed one slide. Okay. So the real power of quantum computing comes from this idea of the qubit. And what the qubit is it's like a regular bit of information, which we normally think of as a 0 or a 1. But it doesn't have to just be one of those two states. So here in my diagram, I've actually shown the bits of information as a -1 and a 1, but that doesn't really matter. The important thing is that there are two different states, and I'll explain why I use -1 later on. So you can just think about them as 0 and 1 if you like. But when you have a qubit and you have access to quantum physics, you can put this bit of information into what's called a superposition state. And what that actually means is that the bit of information hasn't quite decided yet which of the states it wants to be. So some people think about this as the bit of information being in both states at the same time, but I don't like to think like that because it's a little bit confusing. It's much better if you think it's a bit of information that hasn't decided what it wants to be yet. So the possibilities are open to it. It could become anything, okay? It could become either a 0 or a 1, whichever it chooses, depending on what you do to it. So keep that in mind as we continue on. So how can we compute using these resources? So if you remember back to the previous diagram with the logic program, we took some bit strings in, we applied a program to them, and we got some transformed bit strings out. So with the quantum computation, what you do is you start with these quantum bits, which haven't decided what state they want to be in yet. And you apply to them, instead of a logic program, you apply what's called an energy program. And then what you get out at the end is all those bits end up deciding whether they want to be in one state or the other. Here I put -1 or 1, okay? So by applying some program to this set of qubits, you're able to get them to all decide what they want to be. And it's actually that program it's kind of the difficult bit is crafting that program and knowing exactly how to make this configuration of 1s and -1s actually mean something in the real world. But hopefully in a little while, I'll kind of explain to you how you get those 1s and -1s to mean something in the real world. So remember, so at the start, the qubits haven't decided what they want to be. And at the end, by the end, the qubits have decided what they want to be. So really, they're no longer qubits anymore. They're just regular bits of information that have chosen which way to be. So what is this energy program that I'm talking about? What are you actually doing to the qubits to make them go from one state to the other, to transform them in this way? So here's a very kind of high-level graphical picture of what an energy program is. So you take this bunch of qubits and you apply to them some numbers, which are, here I've called them H and J. And I'm going to show you on the next slide an example of what the actual numbers look like. But what you have to remember is that there are two different sets of numbers that you can apply, which forms your energy program. So the pink values here are known as the H values, and what these are is they're little numbers that you apply to the qubits themselves. Okay, so that's why I've drawn them as circles around them. And then the J values, which are the green lines, are the values that you apply to the connections between the qubits. Okay, so you've got all these little things that are biasing your qubits, and then you've got all these green things that are biasing the connections between them. And so that collection of numbers is the energy program. So let's look at this graphically a little bit more carefully with some real numbers. So here I've kind of shown the same thing, and you can see that here the energy program really is just a bunch of numbers. So you can see that with the H values, I've applied some numbers to them, and with the J values, the green things, I've applied some other numbers. And these numbers can be positive or negative, and that's important. And it relates to this -1 and 1 thing that I was discussing earlier. So this is basically an energy program, which is kind of cool. So you might ask, well, what does it do if you run this energy program on the quantum computer? The answer is I have no idea. I just made these numbers up. Okay, so it probably doesn't do anything interesting. I mean, it could be some really interesting mathematical problem, but it's probably not. It's probably just a bunch of random numbers. Okay, so let's see what actually happens inside that that energy program black box, the E box I showed you earlier, when you actually apply this energy program to your qubits. So again, you can see kind of the same idea. You're going from the qubits in the superposition of state, which is the ones I've shown in pink, to the qubits having decided which states they want to be in. So the way you actually do this using the quantum computer is you slowly turn off the term, the kind of term that makes them want to be in this superposition state, that makes them want to be undecided. You slowly turn on your energy program at the same time. And what that means is that the qubits decide which state they want to be in, subject to your energy program. So your energy program is the thing that causes them to end up with that particular answer, that causes them to end up being -1s or 1s. Now, the trick with energy programming is to craft that energy program, those bunches of numbers, so that the answer that you get out actually means something. Okay, so it has to be meaningful. So if I just put my random numbers in, like I showed you before, you'd get some of these values of these -1s and 1s, but that really wouldn't mean anything in the real world. So later on in the programming tutorial, I'm going to show you how to actually program this thing, craft an energy program that really means something. So that should be kind of interesting to see. So first, I'm just going to take you on a little detour through what these qubits actually are. Because up till now, I've been showing them as these little like pink dots, so it doesn't really mean anything, okay? They're just like graphical symbols. So I'm going to show you how they're actually built and how they're actually made, and how we put them together to make a real processor. Because I think it's interesting to see some of the graphical, some of the actual photographs of the chips and the processors themselves to get a real idea of what these things look like and what they are. So we know that regular computers encode bits of information using like voltages on small transistors inside the circuit, the integrated circuit. So how are quantum computing bits different? So here is a diagram of a building block of a natural quantum computer. And this is called a superconducting qubit. And the reason that it's a qubit is actually because of the material it's made of. So you know how you make transistors out of sort of semiconducting materials. And what this means is that you can have the physics of the transistor basically means that you can end up with it encoding a 0 or a 1 bit of information. With a superconducting qubit, it's kind of a loop of superconducting metal. And what happens when you cool a loop of superconducting metal is you get these interesting magnetic field states that can be point up or point down, like I've shown in the diagram there. And these little magnetic bits of magnetic field are actually can encode that information. So instead of using a voltage state like you do in a transistor, you use a state of magnetic field, either pointing up for, say, +1 and pointing down for -1. But the interesting thing about superconducting qubits is that when you cool them, they start to demonstrate and they start to exhibit quantum mechanical effects. So what you find is that those little magnetic bits of information are no longer just pointing up and pointing down, but you can actually control this object so that you can get them to be in a superposition of those two states. So you can adjust a control knob on your quantum computer and you can put this object into that superposition state where it hasn't yet decided whether that magnetic field wants to point up or down. Okay, so that's basically the building block of the qubit. So that's how we create large-scale processors. We put lots and lots of these together. So here's another schematic illustration of how you start connecting these things together to form a fabric which you can start to program. So that was just one I showed earlier. There are actually 8 here. So I don't know if you can like try and see them or work out where they are, but the long kind of gold rectangular strips that you're seeing are now the qubit loops that have been stretched out. And at the places where they overlap, there are these blue circles, and these are now the connectors between the qubits. So you can see here that there are 8, and I've put on little magnetic fields pointing up or down to represent how many bits of information there are in this system. And the things that you can program are each of the gold things and each of the blue things are a programmable element. So now I'm going to show you what thing actually looks like when you start to build it and design it to run on a real processor. Okay, so you can see now it looks a lot more complicated than it did in the previous diagram, but hopefully I'm building up this slowly so you can kind of try and understand what's on the chip, even though it kind of looks really complicated to begin with. So now the long loops, the gold loops that you saw in the previous picture are now the pink things, and all the green stuff and the yellow stuff in between those pink things is all the circuitry that accompanies the qubits, and that means you're able to control them and program them. So you can see there's actually an awful lot of complexity that goes into building one of these circuits. It's not just making qubits, you have to make all the associated circuitry to actually make the system programmable too. So if you look at this diagram kind of a little closely, you can see loads of yellow dots. I kind of like this because it looks a bit like a city to me, so I think it's kind of sort of fun to look at. But all these yellow things that look like little buildings or something, these are actually the programmable units that allow you to program those H and J values into the quantum computer. So when the processor is operating, all these little things are like little switches that are turning magnetic fields on and off in order to both set your energy program, that's your H and J values, and also to run the quantum computation itself. So you need circuitry to slowly turn on the energy program as well as to specify it in the first place. So there's a lot of complexity on this, and it's pretty cool. Okay, so let's see what these things actually look like when you actually build them on a real chip. So here we go. Here's a picture of real chips that have been made on a wafer in a foundry, which is a place where you send off your design and you get the processors fabricated. So there's actually quite a few of them in this picture, and the largest one actually contains 128 qubits. And you can kind of see it in the sort of bottom middle. It's the little fabric that looks like a bunch of shreddies put together. So the way that we make these processors is that we take all the knowledge that we know from the semiconductor industry, and we use that to build these superconducting electronics. And it's kind of interesting if you think sort of how much effort over the past few decades has gone into building up semiconductor circuits to get to, Pentium 4s and the latest sort of ARM processors and things like that. It's really a lot of effort and a lot of money has gone into this. So trying to build this new type of computing from scratch using superconducting electronics requires an almost similar effort, which is a lot of funding and a lot of research going into how to get these processes to work. But what you get out is processors or chips like this that look kind of almost similar to the standard semiconductor chips that you'd get from a semiconductor foundry. So let's see. What we do next is we take one of these chips, cut it out from the wafer, and we place it in the center of the kind of, if you like, the quantum computer's motherboard. So you can see here it's been placed down on the motherboard, and all these sort of wires have been connected to it to bring down the signals down from the outside world to the processor. The cool thing about this is, if you think about how many of those little programmable elements are on the chip that I showed you earlier, there are literally hundreds of these, if not thousands of them. But you have to control all those little programmable elements with a small number of wires, because you can't bring thousands of wires down into a processor. It's just not possible. So there's actually part of the complexity of that kind of circuitry I showed you earlier is to sort of route those signals so that they go to the right places, bringing them in through a smaller number of wires and kind of like multiplexing them out so that they can address all those individual components. So that's part of the complexity. So once you've put your chip onto your motherboard, you can then put it into the equipment and the system that cools it. So here's a picture of, it's the same thing as before. You can see the gold thing in the middle is now where the chip sat. It's actually underneath that kind of gold protective shield area. And all the wires that you're seeing now are what bring the signals down onto the processor. So you might think this looks a bit weird for a computer motherboard. And the reason it looks so weird is because the thing has to be cooled to very low temperature in order for the quantum mechanical effects to start to come into play. So what we find is that with these superconducting qubits, we have to cool them down quite close to absolute zero to actually get the quantum mechanical effects to show up. So when we're running these processors, they're running in this kind of configuration, like in the picture, inside a giant refrigerator, which runs at a temperature of 20 millikelvin. So that's 0.02 Kelvin, as I put on the slide. And just for some reference, the temperature of interstellar space is 2.7 Kelvin, which is pretty cold. So you can see that these things are actually, these computers are operating at temperatures which are colder than any known place in the universe. I mean, I think that's pretty cool. It's pretty impressive that we're able to engineer technology that can do this and to kind of harness these quantum mechanical effects. So as I said earlier, everything changes when you start doing quantum computing. So it's not just the processors and the motherboard that changes. All the equipment that you need to support the computer and all the infrastructure that you need to help also change. So here I've shown a picture of, now I like showing this because if any of you have kind of like high performance desktop PCs, they usually come with these like funky gauges on the front that show, you know, things like fan speed and like core temperature and stuff like that. So I was thinking this is the kind of display that you get on the front of a quantum computer. And what this is showing is it's showing the some readouts of the vacuum system. So this is part of the system that helps the coolant flow around the quantum computer, and you need to operate kind of heavy-duty vacuum pumps to push the coolant around. So you get these kind of cool readouts on the front of your computer. So really, everything changes from the materials you make the systems out of, all the way up to all the infrastructure that you need to run one of these things. So when we put all this together, what does it look like? So it looks like this. It actually looks like a big black cube. And it's kind of a rather impressive object. It's about 10 feet by 10 feet by 10 feet. And actually, through the power of virtual world technology, I built one in the environment we're in at the moment. So if any of you hang around after the talk, you can go and see the virtual life-size version of the D-Wave 1. So you can like move your avatar around it and things, which is pretty cool. So the reason that I'm showing this is to kind of get across the idea that these are not like desktop PC machines. They're actually will form something that's more like a quantum cloud. So you can imagine these systems being housed inside data centers, and then people actually send their problems to them over the web. And they have lots of capability for queuing problems and handling multiple users at the same time. So you can actually have lots of people using one quantum computer simultaneously, but not in superposition. So just to make that a little bit more explicit, here we go. This is a schematic diagram of how you actually use the thing. So you sit at your desktop PC, and then you connect to our quantum server over the internet, and then that actually sends all the signals into the control system, which convert your program, which you may have like written in a high-level language, down into the machine code, these H and J values that the quantum computer actually talks in. So the important thing here is that all this is really done for you. You just need to sit there with, you know, a Python console or something and actually type stuff, and then you send it off, and you can program the quantum computer. You don't need to be in the lab like turning controls and fiddling with stuff like that. It's all kind of done for you with a high-level interface. So that's what I'm going to show now. And so this is kind of the second half of the talk, which is I've sort of like showed you how and told you how easy it is to program this. So why not like actually show an example of doing this? So for the very first time, I'm going to try and show you how to program quantum computers. I don't think this has ever been done before. And I'm going to try and show you how to learn energy programming and quantum computing in less than 10 minutes. Right, so as I said before, you use a high-level language to talk to the quantum computer. So in these examples I'm going to be showing, I'm going to be using the our Python API. So don't worry if you don't know how to code in Python, because I'm going to sort of talk through the examples, and it's more like pseudocode. It should be fairly easy to follow. You don't need to know any complex programming stuff. Okay. So you might ask, if you had a quantum computer, what's the very first thing you'd program on it? And so anytime you're learning a new way of programming, the first thing you try and do is write hello world, okay? So because this is a quantum computer, we call the program hello multiverse rather than hello world. Okay, and so first I'm going to say a little bit about what the program is by describing the diagram on the right, and then I'm going to explain how you code that. So if you remember from earlier, we had the these qubits, and then we applied these H and J values to them, and that was our energy program. So what I've done here is I've shown 4 qubits connected together, and I've numbered them with the white numbers. And then the H and J values I'm going to apply are the pink and green numbers, following the same convention as before, the coloring convention. Okay, so you can see that what we do. So let me just say, to this energy program again is just random. So I selected these numbers at random. It doesn't mean anything. Okay, it's just a bunch of numbers, but it's going to show you how to use the interface. So the first thing we do is we use Python to import the API, which gives us access to all the high-level functions that you use to talk to the quantum computer. So that's what the first line of the code does. And then we make a connection, which is kind of a virtual, it's like a handle for connecting to the quantum computer so that you can talk to it using Python. and then you create a solver. So there are different solvers that you can use. You can kind of maybe test if your program is working with a software solver before you send it off to the real hardware. So you can choose whichever solver you want. So here we just send a command that passes the chip name as a parameter, so that the program knows and the quantum computer knows that you're actually sending the problem to the real hardware. Okay, then to define the problem, we need to somehow put our energy program into the system. So we just create a vector of H values and an array of H values and a dictionary of J values. And so don't worry about the reasons why you use these particular conventions. All you need to know is it's a way of getting your H and J values into your code. Okay, so what I've done here is I've put in the 4 H values, which correspond to the pink numbers being applied to each of the qubits, 48, 53, 52, and 49. And those values are 0.5, 0.5, minus 0.5, and minus 0.1. And then the same with the J values. And again, if you know Python, you'll see the reason you need a dictionary to specify the J's is so you can tell it which pair of numbers it has to put this number between. Okay. Right, so what we've done here is we've now programmed in our energy program into the quantum computer. So what we want to do now is use the quantum computer to solve this problem. So apply this energy program to those qubits and take them from the state where they're undecided to the state where they are decided whilst applying this program. So now we send the problem to the hardware. So I've just told it to solve this problem using the H and J values I just sent it. And the number of reads is the number of times that it repeats the computation to get some statistics. And I'll explain why you need to do that in a minute. And then, so what I've done here is I've just pulled the answer back from the system. And then you can see I've put print the number of the qubit and the answer. So remember, the answer that comes back is whether the qubits are -1 or 1. So what you get back in your console or your IDE or whatever is these values, which you get, -1s and 1s coming back. So you've actually solved your very first, you've ran your very first program there and solved something quantum mechanically, which is pretty cool. And these -1s and 1s are the best configuration that the quantum computer found, subject to your energy program. And speaking of the multiverse, if you like thinking about the multiverse and parallel universes and stuff like that, you've just created 2 to the power of n universes on your quantum chip. So here n is equal to 4 because we had 4 qubits. But when you're using the full chip, you can actually create 2 to the 128 different parallel universes during your programming, which is pretty cool, I think. So I showed you how to write a Hello Multiverse program, but it's kind of boring because we're just sending random numbers to the quantum computer and getting some answer back that doesn't mean anything. So the next little tutorial I'm going to go through is to show you how to do something that's actually a real programming, a real program. So as I said before, the first thing that you have to understand when programming a quantum computer is to think in terms of energy. So forget everything that you know about, programming. This is completely different, and this is a key. If you can kind of get this, then everything becomes clear, and you can think about a totally new way of programming. And the key is whatever problem you want to solve, or whatever thing you want to simulate or do, you have to transform it into something where minimizing the energy will give you the correct answer. So the thing is, it probably doesn't mean anything when I just say this, but if any of you go on to start learning energy programming and doing quantum computing in the future, this slide will be to come back to. So remember that you have to craft this program in terms of minimizing energy. I'll explain what I mean in a minute. So what can we energy program from scratch in 10 minutes? So let's choose something very, very simple, which is simulating a circuit element called a NAND gate. So what's a NAND gate? So a lot of you probably know what a NAND gate is already. It's a little building block that we use in conventional computing. And you can see here I've shown a little graphical representation of it. What a NAND gate is you put some values into the inputs. So here they're A and B, and you get some value out of the output, which is C. And these values can be true or false, which I've shown as F's and T's in the table. So you can see here on the first line, if you put false into A and false into B, you get true out of C, and etc., etc. And the reason it's called a NAND gate is actually because it's a not AND gate. So what an AND gate means is that if you have the same inputs, if the inputs are the same, then the output will be true. But because this is a NAND gate, it's like the opposite of that. So if the inputs are the same, the output will be false. So this doesn't really matter. I've just picked a gate at random. You can actually pick any old gate, but this is kind of a simple one to start with. And I'll actually explain why I picked this gate a little later on, which is kind of interesting. So this is the logical way of thinking about a NAND gate. What we're going to do now is we're going to do a bit of paradigm shifting, and we're going to try and write this as an energy program. So here we go. I've actually already given you the answer here, so you don't need to do any work, but I'm going to have to do a little work to explain what the answer is. So what I've done now is instead of, I've written out every possible combination of A, B, and C values you can have. Now, that's whether or not they conform to this NAND gate convention. I've just written out every possibility, okay? So you can see that in here, the NAND gate is actually kind of hidden in there somewhere. I'm just looking at the A, B, and C columns for now. You can see that out of all those possibilities, the NAND gate is in there. It's like some of them correspond to the table I showed you earlier. So what the job of the energy programmer is to do is to find an energy function so that using these A, B, and C values, you can actually capture those ones that correspond to the NAND gate by making them take a low energy. So the energy function I've shown there is actually kind of an expression which uses those A, B, and C variables, and you can multiply them together. You can do whatever you want with them. You can add them, subtract them. But the thing you come up with has to be so that when the inputs and outputs belong to that NAND table I showed you earlier, the energy function is the lowest. Okay, so I've kind of given you the answer here. It's actually this like minus A minus B minus 2C plus AB plus 2AC plus 2BC. That's the energy function. Well, it's one energy function. There might be others, but you can see when you plug in these values of A and B and false and true, and in this case the false and true correspond to -1 and -1. Sorry, -1 and +1. I just call them false and true because it's easier to see in the table. Okay. So when you plug those values of -1 and 1 into this energy function, you get these numbers out, which are in the fourth column. And you can now see that whenever the NAND configurations turn up, the energy is the lowest. So we've actually captured the NAND gate in an energy function. Okay. So now what I'm going to try and do is I'm going to take this energy function that I've crafted. So there's no programming yet. This has all been done on the back of an envelope with a pencil. Okay, I'm going to take this energy function and now I'm going to program it into the quantum computer. So how do we do that? So back to the kind of diagram we had before with the connected qubits. So this time there are 3. I've just used 3 because we have 3 variables, A, B, and C. And what I've done is I've written out the energy function, and now I've taken the coefficients of the energy function and I've highlighted them in pink and green. And the reason for this is that the values you want to apply to the qubits, i.e. the pink values, are the coefficients of the names of the variables. And the values that you want to apply to the connectors, which are the green values, are the coefficients of the products of those variables. So you can see if you get an A, B multiplied together, then the coefficient is 1. So we want to apply a 1 to that J value. So I've written these out in the little box underneath. Now, when I put these into the energy program on the right, you can see that I've actually scaled the values down. So they're still in the same ratio, but I've divided everything by 10. So you might say, why have I done that? That seems like a silly thing to do. So let's see, why did I do that? So if you remember before, we had 4 qubits in a square. That was the thing we were programming. And the reason for this is that this is how they're actually connected on the chip. So in the example I just showed, you actually had to have a triangle of them. And we've actually got a square. So I have to think, well, how can I change a square into a triangle? So what I did was, if you look at the diagram on the right, I just picked 2 of the qubits from the square and I made them the same. And this makes them what's called one single logical variable. So I've locked those 2 together. So you've effectively got a triangle because 2 of the corners of the square are now acting as though they're one single bit. Okay. And you find that you have to do this a lot with energy programming. So it's just one of those things that you have to kind of figure out a way to do. And the way that you lock them together is that you make the value of the connector much stronger than the other ones. So now you can see why I had to divide all the others by 10, because I want this connector that goes between 52 and 49 to be very strong. So I made that -1, so it's a large value. And all the other values are small compared to that. So now what that's effectively done is made a triangle out of our square, because the qubits that are called B are now effectively acting as the same bit. So what we did was, let me just go back one slide. Yeah, so here again, we've done exactly the same thing as we did before with programming these H and J values. Sorry, I skipped one slide there by accident. Yeah, this is the one we should have been looking at. So we programmed in these H and J values just like before, using the same code. They're just different values this time. Okay, and you can see again, there's the -1 in the J between 49 and 52 that makes the 2 locked together. So we've now programmed the energy program in, and now we send the problem to the hardware, and we print the answers out. And what you can see is the answers that come back are again a bunch of -1s and 1s. So remember now that 52 and 49 are locked together, so the outcome should always be the same. So here it is the same, it's both true, so that's correct. So the actual answer should be false, true, true. Okay, so false from the first one, 48, true from the combination of the second one, 52 and 40. Back at our energy NAND gate table and see if this is right. Right, it's correct. So you see, what happened here is the quantum computer found this particular answer from the energy NAND gate table. So it's actually picked out a set of values for A, B, and C that are the same as what you'd expect to get from a NAND gate. So you might think, well, that's only one answer, but you know, to get the full NAND gate, you should be getting all 4 of those. And you actually do get all 4 of those. So if I just go back one slide, if you look at the line of code that says answer equals, and then you can see at the end it says solutions 0. What that means is I picked the first element of the solutions. But the chip actually returns lots of solutions. In fact, here I've done 100 reads, so it will return 100 solutions. And if everything's working correctly, those 100 solutions should be all from these 4 correct answers. So it will always either return false, false, true, 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 false, true, or true, true, false, okay? No matter how many times you run it. So every time you run the quantum computation, you get a sample which will be one of the answers, and they'll always correspond to the NAND gate truth table. So I don't know if that makes sense at all, but what I've actually done here is I've used the quantum computer to encode a NAND gate. Okay, so you might think, what's the point of doing this? Because we already have NAND gates that work quite well. So why have I gone to all this trouble building a quantum computer to simulate a NAND gate? Well, there's two really interesting and important points to note about this example that I showed you. So the first is that the NAND gate is a building block for conventional computers. And actually, if you string enough NAND gates together, you can build a conventional computer. So the cool thing about this is I'm actually able to simulate conventional computers using a quantum computer. Anything I can do on a conventional computer, I can do on a quantum computer with enough qubits, just using this method of building gates, which is really cool. So that's, obviously you wouldn't do that because there are much more efficient ways of building conventional computers like the way we have of doing it. But it just shows you that you can do anything with energy programming if you kind of put your mind to it. So the second thing to note about this example, which is even cooler than the first thing, is that the NAND gate is actually reversible. So let me just go back. So you can see here, there's now no difference between inputs and outputs. They're just A, B, and C. So the quantum computer doesn't care whether your thing is an input or an output anymore. All it knows is an energy function, okay? So you can like run the NAND gate backwards if you want. You can put an output in and see what comes out of the inputs, which you can't do with conventional NAND gates at all, because they won't work. So the cool thing about quantum computing, and this is an example of it, is that it's actually a reversible form of computing to some extent. And what reversible computing means is that you get, it's much more efficient because you're not losing as much information when you go from input to output. So you don't waste as much energy. So I'm not going to go into that in detail, but it's just a useful thing to note. So I've probably like scared everyone now with energy programming because that seemed like a lot of effort to go to just to simulate a small gate. And it really is. But the thing that you have to remember is that when you're energy programming, you can actually write much higher level applications. You don't have to do everything by starting with gates and working up. There are actually energy programs you can craft to run much higher level applications quite easily. So one thing that fits very well into this sort of paradigm of programming is using quantum computing and energy programming to do machine learning. So what's machine learning? Well, it's the discipline of teaching computers how to learn from experience. So most of the programs that we write are very static. You know, you write some code, you run the code, and it will do the same thing every time. With machine learning, what you can actually do is get computers to modify their own code so that they can learn from experience and learn from new pieces of data that are given to them, okay? So this is kind of part of the idea of artificial intelligence. So it's kind of one branch of artificial intelligence. So I'm now just going to kind of give a brief overview of how you can use energy programming to do AI and machine learning on the quantum computer. So first, let's just recap with our diagram from earlier. So this is kind of trying to get you to think, why should energy programming and this method of running a quantum computation be good for learning? What's the link there? So let's just look at this diagram again. You can see that the bits that haven't decided what they want to be yet get some program applied to them, and then they end up in a configuration which is good for something or other. Okay, so I don't know if this reminds anyone of anything. It reminds me of something really strongly, which is the way that we do learning in the human brain. So if you think of the human brain as being a collection of little neurons and synapses that connect the neurons together, at first you have a massive kind of cluster of these things, and they haven't decided yet how to be connected. They haven't decided what strength they need to fire at to kind of do something useful in the world. But over time, if you supply enough data to this system, these neurons and synapses end up in a particular configuration that's good for some task. So we can start to see that actually finding a good configuration of bits of information is really kind of quite strongly linked to learning. So now I'm just going to very briefly, I'm not going to show you any code for this part, but I'm going to kind of explain at a high level overview of how you start to do machine learning and energy programming on the quantum computer to exploit this similarity to the way that the brain learns. So you might think it sounds like writing the energy program for something like this would be really complicated. I mean, we have no idea how things like the brain work and how we learn. So how on earth would we start to craft an energy program to capture this and represent it? Well, it turns out we don't have to, because there's a mode which you can use the chip in, which is known as learning mode. When you do this, the system can write its own energy program, okay? So the way that this works is, I've kind of shown an example here. So you start by showing the computer lots of examples of the thing it has to learn about. So here I've shown it pictures of different types of fruit. And what it has to do is try and learn by seeing an image of a fruit, what type of fruit it's looking at. Okay, so the way that it works, the way that this algorithm works now, is that the program at first doesn't know what the energy program is, and neither do you. So it starts by guessing a random energy program, which is why I've put a question mark there. Just picks some numbers at random like I did earlier. And then what it does is it repeatedly runs the quantum computation. And at first it gets out gibberish, but over time, what you can do is it can slightly start to tweak and modify its own energy function until it finds one that gives out the right answer. So what I've shown here is lots and lots of example fruit going in to the system, and you're running the quantum computer over and over and over again. Each time it's finding a configuration of outputs which represents, so say you sent in a picture of an apple, it might say like raspberry, it might get it wrong, but then it gets penalized for that. So the next time it tweaks its energy program to try and not do that again. It keeps doing this over and over again until eventually it's getting all the answers right. And so these are examples where you've told it what the fruit are. So you know it knows when it's getting the answer right. And once it gets all those right, you can then move into what's called the testing phase in machine learning. And what you do now is you show it an example it's never seen before. And you can see now I've replaced the question mark with an E, because now it's found a good energy program to do this task. So I show it some apples, but I don't tell it that they're apples. And now it runs the quantum computation just once, and you can see that the configuration it comes up with is a configuration that represents apple. Okay, so again, you think of how this is similar to the brain, because what we do is when we see a picture of an apple, set of apples like that, there'll be somewhere in our brain, there'll be a kind of set of connected neurons which fires to represent the label apple. So that's really what the quantum chip is doing. You send it in a new image, and the qubits all light up in the correct configuration to mean apple. Okay, so you haven't had to really write any energy program at all. The computer's written its own energy program, which is pretty cool if you think about it. And so the reason that quantum computing helps with this, because you can do this with conventional computers, but conventional computers don't have the quantum mechanics to help you do that step of finding the good configuration. So this is something you have to do. Let's go back one. You have to keep doing this over and over again, iteratively, to get it to learn the energy program. When you try and do this with conventional computers, it doesn't work very well because they're not good at finding a good configuration. When you do this with quantum computers, they're much better at finding that good configuration. so they can learn to represent things much more accurately and much faster than conventional algorithms can. So one last thing I wanted to note about this, and this is kind of cool and it's subtle, which is, if you remember before when I showed you the NAND gate example, the system returned more than one solution. And that's what we wanted, because we wanted it to return all the solutions that corresponded to the NAND gate, to encoding the NAND gate correctly. So what happens with that when you do something like this learning activity? Well, you find that you also get multiple solutions coming up. So you might think that's a bad thing because, well, if your system said apple and it was actually a picture of some raspberries, you might think that there's something faulty with your computer. But there's actually a lot of hidden information in this. So if your computer returns the wrong solution, what it's actually saying is it's not very confident in the answer. It doesn't know for sure, okay? So you can actually, by running the quantum computer in this multiple reads configuration that I showed earlier, out of those 100 answers, you're actually getting some information about how confident the computer is in its answer. So if it returns apple 100 times, it's pretty sure it's an apple, okay? But if it returns apple 50 times and raspberry 50 times, then it's probably not so sure, and you've probably got some stupid image that looks a bit like an apple raspberry or something you're feeding in. You can try and confuse it and check all this. So that's really cool, because as people, we don't work by having definitive yes/no answers to things. Sometimes we're unsure. And so this quantum computing framework is a way of capturing that uncertainty in answering a question about the real world, which is also really, really powerful. In the machine learning parlance, this is known as Bayesian methods. So if anyone's familiar with that, this architecture fully supports Bayesian methods for learning. So I hope that this has all been very interesting that I've shown you so far. I'm gonna finish with a little thought experiment. So I noticed that someone earlier in the text chat mentioned like cryptography and things. So I often get asked the question, so aren't some computers supposed to be used for factoring numbers? And I say, well, they can be, but the way that we're building quantum computers is much better at these sort of learning tasks than sort of like factoring and theoretical math type problems. So I'm going to leave you with a couple of scenarios. So imagine two scenarios. The first one being that humanity builds quantum computers and they're able to factor very large numbers. Isn't that awesome? We've solved some mathematical problem. That's very cool. The second one is that humanity builds quantum computers and then we're actually able to train them to intelligently learn things about the world and solve all these problems that we're currently having with conventional computers, such as doing better image recognition, having systems that can learn natural language in the way that people do. Just having computers that learn more like people do in general and can have all these things like uncertainty in their answers and able to change their program over time and learn from experience and all these other cool things. So I personally think that the second one is much more interesting, but I'll leave it up to the viewer to decide on their particular opinion. So that's the end of the talk, and I just want to put a little plug out for our blog, which is called Hack the Multiverse. And you can visit it by going to the D-Wave website or just typing dwave.wordpress.com. And it's there's actually a link to it over there on one of the screens if anyone wants to have a look. So that's the end of the talk. I hope that you all found it very interesting, that you learned a little bit about how to program quantum computers. And maybe in the future, you should keep an eye out on the blog, because there might be some ways for you to get involved in the programming of the quantum computers yourselves. So we have a little project in the pipeline for that. So thanks again for listening.
So this was not a canned applause, I did it by hand. It was a really great talk, Suzanne. Thank you very much. And we open now the questions and answer session. And I'm going to start with the first question. Those who have questions can either speak or write in the text chat. But perhaps if you have asked already your question in writing, you should ask it again because it may be difficult to read the text of half an hour ago. So the question I'd like to ask is this. I understand that from your point of view, the most interesting applications are those related to machine learning. At the same time, I don't think that any really exciting application to machine learning is very close. And I wonder what could be the first commercially viable application that show that something which is very important can be done with quantum computer much better than it can be done with conventional computers.
Mm-hmm. So this is an interesting question. I think that, like as you say, machine learning is a very difficult field, and there's still a lot of research going on in it. The way that I see quantum computers being applied is kind of in a modular way. So you start by writing a very small application that does one thing very well. So as an example, one of the things we did was we collaborated with Google on building an image recognition system which detected cars in images. So that was one example of you start very small. So you start just with something that can recognize cars, for example, and then you can sort of build up on that. You then you build an Apple detector and a face detector and everything. And so you have to start with very small applications like this and work up, because the processes at the moment are still quite small scale. So although you can use them to do these learning tasks, we have to wait until the technology matures significantly to do really large-scale learning tasks on them.
We have a very interesting question from user 13 who asked what Lockheed Martin is doing with their D-Wave-1. Maybe Suzanne will not be able to really answer that because of commercial confidentiality, but let's hear what she says.
Well, I can talk in general about what they're doing. I mean, they actually mentioned this in the press release, which is they're using the system to work on a problem which is known as validation and verification. And at a high level, it means testing that very complex systems are working properly and looking for the fault modes in them. So it's basically if you have a very complex piece of equipment, sort of be it hardware or software, there can be bugs in that equipment that you might never know about until you're operating it and something suddenly goes wrong. So there are methods by which you can try and look for those bugs beforehand, so that they don't turn up when you're actually using the thing. And so that's what they're using it for.
Now, Remy Suzanne is asking whether you have any emulators and other tools that can be used to learn quantum computer programming.
Yeah. So I think we're actually working on some projects at the moment that might involve making things available for people to play with in simulators and such. So like I said, it's in the early stages at the moment. So the best thing I would suggest is to follow the news on the blog, and there will be announcements on there as to how that's going and when these things will be available for people to play with.
We have a question from Whopper, also known as Carlos, who wonders if quantum computing can accelerate the development of teleporting technology.
Well, there is a phenomenon known in quantum mechanics, which is quantum teleportation, which is the ability of a quantum state to be kind of delocalized over space. So, for example, if you have two qubits and they're entangled, you can kind of adjust one and the other one will kind of change, no matter how far apart they are. But there are some problems with this. So it's very difficult, or perhaps impossible, to actually find ways of transmitting classical information using that technique. So if you're actually looking at ways to say teleport bits of classical information, it's not clear that you can actually do that with that scheme. But I mean, I'm fairly open-minded. I think that if you look 100 years ago at how people understood physics and you look at it now, there are a lot of things that we really didn't understand back then that we would have thought sounded crazy now. That we can do now, sorry. So, I mean, I don't rule out things like teleportation and things like that in the future. I think it requires a deeper understanding of physics. The quantum computing architecture we're working with doesn't actually really use kind of quantum teleportation in the way that some other schemes do that use photons and things. Our thing is very much more like locally confined information, and you're just finding configurations of it, so we don't have to really send photons large distances or anything like that at the moment. But it's certainly something that could be explored in the future. It's quite interesting.
We have an interesting comment from user 9, who observes that even with simple computation, we don't get 100% certainty of the result, even in conventional computing. And so he wonders, how do you handle doing many computation in parallel where the outcome of each computation depends on the result it gets from the other computations?
So let's see. I mean, if your circuit is working correctly in conventional computing, you do get 100% certainty. Where we don't is when we actually kind of try and bake into the algorithms you know, trying to get uncertainty. We have to actually program it in explicitly. Like we have to use random number generators and things like that. But if you, in a conventional computer, if you put the same program through a digital circuit, if your circuit is working as it's supposed to work, you will get the same answer. So the thing is, with quantum computing, you don't. It's actually, the randomness is much more fundamental to the computation. We don't have to build quantum computer random number generator equivalents to try and get that randomness. It's actually just there, and nature gives you that. So that's and it sounds like a bad thing at first when you think, oh, my computer's giving me different answers every time. But when you start looking into these learning tasks, it turns out that it's really useful to actually have that source of randomness and to not get the same answer every time. It's kind of, that's in a way how the brain works, is by exploiting that randomness. What was the second part of the question? When many computations depending on each other. So I'm not sure if it gives you increasing uncertainty. I'm not sure I don't think I understand the question very well there. But one of the things I can say about the quantum computing architecture is that these connections between the bits allow you to capture a lot more of the structure of the problem. In a lot of kind of conventional learning approaches, you try and figure out what each bit should be independently, and that's means you're throwing away a lot of the information because bits could be dependent on each other. So an example is like a raspberry looks a bit like a blackberry, okay? So you can actually use that piece of information when you're learning. If you have a connection between raspberry and blackberry in your architecture, you can actually use that to help the system decide what the thing is. Whereas in conventional machine learning approaches, it's actually a really hard problem to take those kind of connections between labels into account. So that's one of the ways that a system helps.
Okay, so now waiting to see if a user 9 wants to add something. We have user 14 who is wondering if any progress has been made towards something like a set of general purpose registers of quantum computer architecture.
Mm-hmm. So the one thing that I kind of discussed before in a couple of the talks I've given is this idea of general purpose computing versus special purpose computing. And the thing with general purpose computers is that they're very good at a broad range of tasks. But when you have very specific tasks that you care about, they're not very good at it. What you do is you sacrifice the broad nature of it, the generality of the machine, for efficiency and speed at particular tasks. So I mean, although the kind of computers we have nowadays can run all these different types of applications, they're just not very good at learning. And the reason why is that what's happening in learning is it's a very specialized mathematical problem that's being solved. So what we're doing is we're trying to build more computers that are more specialized. So it's a bit like the example I like to give is like graphics processing units. So inside your computer and like your Xbox and things, you have a dedicated graphics processor. And the reason is because the regular CPU, whilst it can do those calculations, it doesn't do them very efficiently. So they're farmed out to a special purpose processor, which is much, much more efficient at doing them. So the way I like to think about quantum computers is that they're kind of like special purpose processors for learning and AI. So if you imagine nowadays you have a computer and it has a CPU and it has memory and it has a graphics processing unit. Imagine if it also had an AI coprocessor that it could farm out learning tasks to. And so I think that processor, the quantum computer, is a very good candidate for that kind of processing. So I think, you see, the quantum computer's probably not very good at doing the general purpose tasks like running Excel. But the reason for that is exactly because they're so very good at doing these specialized learning tasks that you've had to sacrifice that general purpose nature in order to get them to be very good at these tasks. So I don't think that we'll ever see kind of general purpose quantum elements in computers like memory registers and things, because to actually harness the quantum resources, you have to be doing them for a really, really specific task.
So we go now back to user 9, who, in follow-up of his previous question, say that if quantum computer can get 99% accuracy on each single computation, what happens after a huge number of computation and how the errors will accumulate?
I see. Okay. So I think I understand the question now. The uncertainty doesn't actually get lower, because if you imagine with the example with the like apple and the raspberry or whatever, if you're giving it an image and it's not sure, then it's going to, if you do 100 samples, then it's going to say apple 50% of the time, and it's going to say raspberry 50 times. Now if you take 10,000, then it's still going to say apple 5,000 times and raspberry 5,000 times. So the uncertainty in what the image is the same. Okay, so it doesn't matter how many samples you take, the uncertainty is still there. It's just more certain about its uncertainty, if that makes sense. So it's kind of it's like a second order of improvement you're getting. So for example, if it was say 0.1% certain that it was a melon, then you probably wouldn't see that with like 10 or 100 samples, but with 1,000 samples, you'd start seeing that it's saying like melon between 1 and 10 times or something like that. So as you increase the number of samples, you get more information about the uncertainty, but the uncertainty is certainly still there.
We have now both Anders and Randall who are wondering what have you done in terms of application to real computer vision problems.
Okay, let me just look at the questions again.
Actually, you could follow up user 9's question with the other question I appended to that, which is, what if you're doing a sequence of steps? Let's say you want the computer to give you one result and you're using an uncertain result, but then you're using that as the input to the next stage in your program. Well, let's say you let it run another program. So you get cumulative uncertainty. I think that's kind of what user 9 is actually after.
Mm-hmm. Well, I don't really know how to answer that question, because I would need to think carefully about the specifics of the kind of algorithm you're describing, where you feed the output from one calculation into the input of the next. So the only thing I can really say about that is it's kind of very similar to the way the brain works. So it's like the system is constantly receiving new information and it's updating its rules about how much it knows. And one of the things that the brain does is that it uses its current knowledge of something as an input to the next time it calculates. So yeah, it's kind of difficult to kind of answer the question because it's not as simple as feeding the output of one calculation into the input of the next. It's slightly more subtle than that. So I can't really answer that at the moment, but we might be able to write some articles on that kind of topic in the future. So it's a long discussion for now.
We have now a comment from Mike, who thinks this is kind of like a dedicated hardware implementation of a neural network continuously modified by a genetic algorithm.
Mm-hmm. Yep, that's almost exactly correct. So it's totally analogous to that. There's a couple of things that are different. So it's not a neural network in the kind of classical definition of one. It's slightly different because all these bits are sort of updating at the same time. So it's like an analog neural network. It's not when people program neural networks in the kind of like formal definition, they have these sort of update rules, and it doesn't really have those so much. It's more of an analog process. So that's one difference. The second difference is about the genetic algorithm. It's actually really deep and subtle insight about this is that genetic algorithms use randomness to help them improve over time. And so what our system is doing is it's doing exactly the same thing, but it's not using randomness from kind of natural selection. It's using randomness from the quantum mechanics itself. So it is exactly like a genetic algorithm, but instead of in a genetic algorithm, you have to kind of program in a random number generator to generate that randomness to then improve your neural network. Whereas with the quantum processor, it's actually using the randomness that comes from the quantum mechanics not knowing, the bits not being decided one way or the other to introduce some randomness into the system. So it's really, really closely related to that, and that's a good way to think about it.
We have a question from a Weaver who is wondering whether two different energy programs can be shown to be equivalent theoretically, like we can show that two conventional computing programs can be shown to be equivalent.
Mm-hmm. They probably can, but I don't know if there's any theoretical kind of formalism around how you do that. I mean, it seems fairly obvious that there are sort of these degenerate energy programs. If you think about the NAND gate, there might be a different way of writing the energy function which captures the same behavior, and it might give exactly the same numbers. So I'm sure that there are, but I don't know how to find those or how to actually kind of decide whether there are or whether there aren't, sort of mathematically. I don't really know about that.
We have a last question from Anders, who wonders how fast we get the results. What is the speed of getting the results? How many convergences to optimal state per second can I get out of the computer?
So it depends on the problem you're running. At the moment, we're able to take several. The actual core computation only takes a couple of microseconds to run. So that would be the time to do the the annealing part that I showed, which is this going from the undecided state to the decided state. So that takes just a couple of microseconds. So you might think that sort of looking at it theoretically, you could be taking a sample every couple of microseconds if you didn't have any other overheads. Now, as we know, all processors and all computers have other overheads with them. So that's kind of the limit on the current architecture at the moment. Now, there's actually, you could probably do it faster than that. And the speed at which you can do it is related to this idea of keeping the energy function in a low energy state all the time. So if you do it too fast, then you might break your energy function. But we've never, running any computations, we never found that that's happened yet. We've always managed to go slowly enough, where slowly is a few microseconds. Of course, there's a lot of overhead on that. So for example, reading out the answer at the end also takes some time, and programming in the problem itself also takes some time. And when you put information into the processor, it heats up a tiny bit, so you have to wait for it to cool down again, and that takes some time. So it's kind of in the milliseconds to do the computation with overheads. at the moment for a sample. So it's not, I mean, that's kind of a little vague, but I'm not really supposed to go into the details of the processor performance metrics, but the actual core computation is kind of roughly microseconds.
We have now a question from the Russian transhumanists who wish to know whether Neumenta's hierarchical temporal memory concept can be implemented in the wave quantum computer.
Mm-hmm. Well, I'm sure it can. There's not kind of a very well-defined algorithm for how to do sort of deep neural net approaches on quantum computers, but that doesn't mean that there isn't one. What it means is that no one's really thought about it yet. So it's actually one of the things that I'm really, really interested in, is looking for ways to do deep learning using these kind of architectures. They're very well suited for it. I don't know if anyone's familiar with the idea of restricted Boltzmann machines, and that you can kind of chain these things together in a hierarchy to make a hierarchical neural network, and the hardware at its core is effectively a restricted Boltzmann machine. So it is sort of intuitively, you might think it's kind of possible to do that and to implement that kind of algorithm. The temporal part I'm not so sure about, because you do need quite a lot of memory associated with that, so you might need to use peripheral qubits that kind of tag along on your neural network, so you have kind of multiple versions of it running in parallel, each remembering a previous state. But like, to actually come up with a formal algorithm that you can then program would take a lot longer. So I think my answer to that is that I think that it is possible, but it needs a lot more research and a lot more work to go into it to really discover kind of algorithm that both fits on the hardware and is efficient.
There is just one more question that I can see in the QE, but if I have missed someone, if you can please type your question again, we may have time for another couple of questions. So what I see is last question from Randall, who asks in which way is MQC more efficient than learning on a Silicon Tech neurocomputer hardware? And he also asks whether neuromorphic processors he also says that neuromorphic processors can produce multiple answers in parallel that compete. And how does this differ from multiple results in quantum computing?
Okay, so the main difference between the quantum computing architecture and the kind of neuromorphic architectures that have been suggested and built is down in the physics, is in the quantum mechanics. So you can actually build hardware that looks very, very similar to the architecture that we have and the architecture of the brain using conventional silicon processors, and then you can run very, very similar algorithms on it. But what you end up having to do is you still end up having to solve this hard optimization problem at the core. And where that optimization problem comes in is when you're trying to do that, the part where it's learning its own energy program. It has to somehow update its energy program as new information comes in. What you find is that conventional silicon processors use techniques to do this minimization procedure that aren't very efficient, and they don't work very well, and they get stuck in local minima. So by using quantum mechanics, you can actually find a better and more accurate solution, and what that corresponds to in my example is it finds a better energy program at the end, so you end up with a more accurate classifier or a more accurate learned program or something like that. So I think.
Okay, and we have now one last question from Tudor, who asks whether the new high-temperature superconductors can help doing quantum computers at higher temperatures than what you are using now.
Mm-hmm. So there's kind of 2 points to note about that. So the first thing with high-temperature superconductors tend to be much more complex materials than the type that we're using. So just to kind of clarify this, the type of superconductors that we use at D-Wave are a niobium. which is a superconducting metal, and that superconducts at 9 Kelvin, approximately. High temperature superconductors kind of superconduct at like 10 times higher than that, so around 90 Kelvin. However, there's two problems with high temperature superconductors. So the first is that even though their superconducting temperature is much higher, you find that the quantum effects still don't occur until you cool them much lower than that. So superconductivity is in itself a quantum mechanical effect, but you need the quantum information, if you like, to be very pure and very quantum mechanical. And you find that even though they superconduct at a high temperature, you still need to cool them a lot further to actually get them to behave properly as quantum mechanical objects. So you kind of don't win there. You still have to cool them down to 20 to 100 millikelvin to get them to work. The second thing about high temperature superconductors is because they're these really complex materials, they tend to have a lot of defects in them when you try and build them into actual like loops, like qubit objects. So what that means is you get a lot of noise and a lot of error in any computation that you try to do with a material that's full of defects and things like that. So what we try to do at D-Wave is build qubits that are as noise-free and as identical and ideal and perfect as possible. And even when you do that, you still have a whole bunch of problems. So you have to start with the most ideal material you can find to build these things, which is niobium. So I think in the future, maybe people can look into using high temperature superconductors, but I think for quantum computing, the moment at least, it's going to have to be the low ones, and we're going to have to stick with the low temperatures.
Okay, first I wish to read aloud the observation of Mike that we are now back to room-sized computers operating in cold basement environments, and since this is the kind of thing that old people our age remember, this means that the golden age is coming back, and that makes me happy.
Yeah.
And we can close with the last question of Randall. You mentioned the problem of wiring the chip to the motherboard. How does it compare with wiring a regular CPU with many internal register bits and communication to billions of memory bits? And if you can still use multiplexing and buses?
Well, you could certainly use multiplexing. You can actually use buses as well and shift registers and all these kind of things, but the important thing is that they all have to be built from this new superconducting electronic technology. So while you can still use all the same kind of ideas and even the same protocols of moving bits of information around, the actual devices themselves now have to be built from superconducting electronics, and they have to use these little magnetic fields instead of voltage states. So really you have to re-engineer everything. So it is possible to do all this, and it's possible with superconducting electronics to bake in all that complexity that you have with conventional computers. It's just that it has to be totally redesigned and refabricated, and all the processes have to be improved to the stage where they're reliable and robust, and that takes a lot of effort and time. But there's nothing that kind of stops you in principle from having all that circuit complexity plus quantum mechanics plus even more improvements, such as the fact that superconductor electronics are much more efficient than semiconductor electronics. So if we can have enough effort put into this area, we're actually able to build computer chips that generate hardly any heat on chip. So we solve another problem there with superconducting electronics. So I mean, it's a really interesting field. I mean, you get efficiency savings, you get quantum mechanics along with it. It's just that we need the effort to go into building these technologies up to the scale at which the semiconductor processes are made before we're able to reap the rewards. And unfortunately, that just means a lot of money, a lot of time, a lot of research. But I think it's personally worth it.
Okay, I think, Suzanne, I hope, Suzanne, you still have the energy for the last question from user 14.
I always have
is
energy.
there some decent... Ah, right, that's great. Is there some decent hope of laser cooling bringing quantum computing out of the mainframe and into the home.
Mm-hmm. So, wow, everyone really wants a quantum computer in their house. It's like we can operate.
Should make it smaller. I don't have space for that.
What's wrong with cloud computing? Anyway, no, seriously. I think that the idea of laser cooling is it's better for cooling quantum bits that are not made from superconducting electronics. So there are other technologies such as ion traps and neutral atom quantum computing. So they haven't really been built at a large scale like this version has, but they've been proposed and small prototypes have been built, and those ones can use things like laser cooling. But the problem is that you find it's kind of like it's like 6 of one and half a dozen of the other. It's like if you manage to improve one technology so you don't need a huge refrigerator, what you'll find is that you need a huge something else. So with things like ion traps, sure, you don't need a massive refrigerator, you can run them at room temperature. But what you find is you need massive laser equipment to be able to control the lasers accurately enough to actually manipulate things. So you can pick any quantum computing proposal you like and try and think about how you could miniaturize it. But it turns out that they all have some complex piece of equipment in them somewhere. It might not be the refrigeration component, but it will be something else. So yeah, that's the problem we have at the moment. In terms of miniaturizing superconducting stuff, I think it's possible. For example, the only reason that these large refrigerators called dilution refrigerators that go down to sort of below 10 millikelvin, the only reason that these things are the size they are is because historically they've been used for research projects. And with research projects, what you really want is you want something customizable. You want something with lots of space where you can put your experiment, lots of wiring, you know, all that kind of stuff, lots of sensors. So these things have typically been very large to accommodate that. But if, for example, technology like this matures further and you know, you're producing hundreds of these things, there's no reason why you can't create a customized small version of it that just captures everything you need for the quantum computation, and you're not using all the rest of this kind of space that's there for kind of legacy reasons. So I think that if you have a dedicated technology roadmap, you can miniaturize things if you know what you're doing. But at the moment, we're still trying to figure out what's the best way to put all these things together. You know, how can we save space, and how can we use refrigerator systems that are commercially available? Because you know, that they're slightly more standardized if you do that. So rather than building your own equipment. So yeah, it's just really a kind of technology roadmap. I think if we pick one technology path and go down that, then I think things start to miniaturize then. And so I don't see why you can't have these things on your desktop in the future.
Okay, there is no other question that I can see, and I think we can conclude the formal part of the talk now. I'd like to upload, and I would like ask everyone to join me to thank Suzanne for this great talk. Great, I'm going to stop my recording now, and I wish to ask the other two persons who are recording, I think Frederic and Jameson,